Now we're going to talk about the kinematics of robot manipulators. So kinematics relates to position and velocity. It's not involving forces, but we want to be able to relate, let's say, where the base frame of the robot is with respect to, where is the end frame of the robot. So first of all, you need to think a little bit about what the arms we're going to look at actually look like in general. Obviously, a robot like this has got a base where it's attached to the surface that it's working on. It could be a table or could even be the ground, a concrete floor or something. And it's quite often used as the origin for the robots, right? If you know things with respect to the origin, how exactly it's specified obviously depends on the robot. But it's the base, it's got stuff in it probably, it's got motors, it's got electronics, and it doesn't move, right? It's fixed to the ground. Then we start having things like linkages. So in this particular case, we've got, here we go, an upper arm, which is basically just a linkage between something happening on the base and moving up to give us an elbow joint, if you like. So this is very much like your upper arm, and this round the base would kind of be round your shoulder in this particular case. Obviously, we've got joints on the robot, which are very important as well. So the links are just a way of translating from one position to another. It's part of the structure of the robot, so it's actually got a real arm, like you'd have your bones and your muscles and everything in your arm. In its arm, it's just got structural components, so it can actually get to different places in the workspace. It might have belts and drive and all kind of stuff in there as well. But basically, joints are the things it's going to move around. In this particular robot, we've actually got Revolute joints, so it's going to be rotating around these joints. So the joints are a very important part of the robot, and they are defined in terms of the axes that we have for them. So here we have a J2 axis, a J3, J4. This is actually rotating round like your arm would. It's also got 5 and 6 as well. Now, the end effectors are a particularly important part of the robot. It'd be, your end effector would effectively be your hand, right? But this is the thing that's you care about the position of. This is the thing that's going to be moving around in the workspace. It may be attached to some kind of tool or some gripper or or whatever it's particularly doing at that point. It could also be doing some welding, but it's the location of that we really care about more than other parts of the robot, right? Because that's where it's actually doing stuff. So a kinematic pair is basically just a couple of adjacent links, and it's the relative motion between them that we're going to be interested in. We're going to be analysing, how do we map from a frame in one particular joint to a frame in another particular joint. This would be a good example of a kinematic pair for this particular robot, so we're interested in working out in the first instance the relationship between axis on joint 2 with axis on joint 3. And we can see this is basically just, it's going to be something which is dependent on this fixed structure that we have to take into account. So degrees of freedom is a way of basically telling you how many links, how many joints a system's got that are basically free to actually do something. So if we have a Revolute joint, then that's going to have 1 degree of freedom. A Prismatic joint, where it's moving in and out, that's also got 1 degree of freedom. If we have a link basically with one axis, so we've got a link with rotating around a single axis, think about, first of all, the link as an object, right? So if that object was free in space, it would have how many degrees of freedom? It would have 6, wouldn't it? It would have 3 translational degrees of freedom and 3 rotational ones. But what we do by putting a link through one of the ends a joint through the end of one of these links, is we constrain it only to be able to rotate around one axis. So it removes 5 degrees of freedom when we do that. So typically a joint, it can only do one thing around the joint. It could be, a Revolute joint, it can only rotate around the joint. So it's only got 1 degree of freedom around the joint. Same thing with a Prismatic joint where something's sliding in and out. The only thing it can go is back and forwards. So a joint gives you a degree of freedom. So typically then, if we have a 6 degree of freedom robot, it means it's got to have 6 joints in it. And quite often that's what we want to actually have. If we want to be able to manipulate things at any position, we need 3 positional degrees of freedom. And if we want to make sure that the tool at the endpoint can actually get everywhere in any orientation, it needs 3 orientation degrees of freedom as well. So quite often you'll see robots are built up to get anywhere in space, but to also make sure that the endpoint can be oriented in the appropriate way. You can actually also get robots with even more than 6 degrees of freedom. In fact, the human arm has probably got about 7 at least. And basically, if you've got 6 degrees of freedom, right, then you can specify the position and orientation of something in space. But if you've got even more degrees of freedom than that, you can do it, but then you've got redundancy in the arm, which means you can do it with different arm configurations. You might be able to bend round one way and do it, or bend round the other way and do it. And this can be very, very useful if you're avoiding obstacles. So this is just basically saying that, if we have a system with n degrees of freedom, and if the number of degrees of freedom is more than the degrees of freedom that you need at the end effector, right, then we call this thing redundant. So this is a good example. We've got an arm now which can get to this particular orientation and position of the end point, or the end effector tool, and it can do it in different ways because it's got more degrees of freedom. It actually needs to just get there in one way, right? So it can actually achieve a particular end effector location and orientation by using a series of different postures. And it may well be that this is very useful, like I said, because you might be able to go round obstacles and things like that. So representation in coordinate frames, we know this before, we've done this before. We're gonna for analysing kinematics of robotic arms, I quite like the arrow way of showing things coming out of the page or going into the page. So if something's coming out of the page, going into the page, you just see the feathers on the back of the arrow, and if it's coming out of the page, right, you just see the point of the arrow coming at you, right? So here is the representation that we used before. In this particular case, I've got an x-axis going to the right, a z-axis going up, and the y-axis, you see the back of the arrow, so it's going into the page. And in this other example, basically, I'm just saying that now we've got y going down, x is off to the left, but now z is coming at you, right? So it's coming out of the page, and I personally quite like that representation. Again, we know that we can build up series of transformations, and now we've understood homogeneous transformations. We can do that for linkages all the way along, and we'll see that in a second. We know that we can represent a transformation between coordinate frames using this kind of way of writing. We have a T for transformation. It could be H for homogeneous transformation, and we always have these suffixes. So from B to A in this case, that tells us this transformation takes us from frame B to frame A, and the one at the top is the one you end up at. And we know also that we can decompose this, if it's a homogeneous transformation, into a rotational component. So there's a 3x3 rotational component in this homogeneous transformation. There is a 3x1 translational component in this homogeneous transformation. And at the bottom we have a row 0, 0, 0, 1, right? And we have to use appended positions. So we have to put a 1 on a position vector in order to be able to multiply this out and get it to work. Now, a kinematic chain basically is a series of linkages which are following on from each other. It's like a path, right, that you're going through. So if this could be an arm, there could be joints at each one of these little nodes, the blue nodes. And what we can do, if we want to analyse this, because let's say we want to know where the endpoint is in the frame of the base. So let's say the 0 frame here, let's say that's going to be our base frame. And we want to know where the endpoint is in that frame. But what we can do is we can say, well, we can break this up into stages so we can actually work it out. So there might be another frame here that we're going to put in. In fact, what we generally always do is when we're actually doing these things using Denavit-Hartenberg convention, we're going to say that we always put the z-axis along the axis of rotation or along the axis of movement if it's a prismatic joint. So we put, in this particular case, we might want to put on this as a Revolute joint, and I'm just sticking on now another axis, another frame as well. So it's got an axis coming out of us, coming towards us, and now we put another frame in. So I'm not really thinking about too much about how I'm doing these frames at the moment. We're just sticking them on just to show you. You can then, you can define at critical points along this mechanism, you can define frames that will help us then finally be able to solve the problem of, where is the last frame, a point in the last frame, how can we get that then back to a point represented in the first frame here. And the way we're going to do it is we're going to say, well, we know what, within this frame, for example, we've got the orientation, of course, but if we said we know the point there in space in this frame of the endpoint is going to be 0, 0, 0, because that's where we've defined the frame to be. Then what we can do is we can say, well, what's the representation of a point in this frame, but with respect to this frame here, the one just before it. And if we know the angles of things and the lengths of things, we can work out that transformation. So then we've been able to get it back to here, and then we can do the same thing again. We say, well, now we've got a representation in this frame, frame 2. Let's work out what it would be in frame 1. And we can do that again, because if let's say we know the angles and we know the lengths of these sections, we can work that out. Finally, we say, yes, now we've got everything in frame 1. Let's work out what it is in frame 0. And if you do that, what you end up with is the representation of the endpoint here. It can also be angle and position, and that's what we're generally going to have, of the endpoint, but we want it within, and we'll get it within the frame at the base. And if we can do that, that is called calculating the forward kinematics. And if we can do that, then this could be a robot. We then know, given this is the base, given we know the angles, given we know the lengths of all the sections, we can then work out where the endpoint will be. And basically, we do it as a product of these individual transformations. So we'd work out the transformation between 3 and 2, then we work out between 2 and 1, and then between 1 and 0. And because this is following the path, they're all linkages, a chain. We can calculate the overall transformation by multiplying transformation between 3 and 2 with transformation between 2 and 1 with transformation between 1 and 0, right? Then we get the overall system out. And because if we're representing these with homogeneous transformations, it's as simple as just multiplying them together. So it's very nice and elegant. So sometimes we're going to have to, rotate frames, and because, they're not always going to be lining up perfectly. So in this particular case, what we see is we've got, let's say, the second frame. How does this relate to the first frame? Well, we can see, right, if we look at the x-axis, first of all, we see x-axis is both in the same direction. So what do we have to do for this frame here to get to this one, right? So what we see is we actually have to rotate around the x-axis. We have to rotate this frame around the x-axis in a positive direction, right? The direction the fingers are going round. If we do that, what will happen is Z will come out at us, and Y, which is going into the page, will end up going up, right? So we could also look at this by hand as well. We could also say, well, the new X value here is the same as the old one. The new Y value is the same as minus Z, right? So this is going in, and the new Z's coming out. And here, the Z value here is actually the same as Y, right? So we could also do that. But this is also rotate around 90 degrees around the x-axis, because we can actually see that that's the case, right? You can see that it's rotating around. So if we put those values in, we'll also get exactly the same value. This would be kind of doing it by inspection. So if we're looking at this then for inspection, you could just put the values in this, right? That's nice and easy to do. If we're looking at here, what we can see is to get the rotation matrix then, x prime, or the x at this point is equal to 1 times the x at this point, so there's a 1 in there. Y prime equals minus z, so we want to have a negative value in there, so we multiply it by the new z, and it gives us back what y prime is, and z prime, this value, equals y. So there's a 0, 1 there to multiply with the y. So just by looking at the axes, you can say, given I want to know what it is in this frame, how does it relate to this? You can just do it by inspection, but you can also stick it in the equation if you want. Another example. In this case, what we see is we've got what's the same? We've got y is the same in both cases. So what's changed now? Well, we can see z here is coming out, right? And here it's going off to the right. So it looks like we've actually done a rotation around the y-axis by 90 degrees. Again, direction of the axis, use your fingers coming round. We can see that then that would rotate the z around and off to the right, and it will also send the x-axis into the page, and that's what we've got there as well, right? So in this case, we see that x is what we had as z before, y is what we had as y before, and z is what we had as minus x before, right? So again, you can also use the formula, but you can basically plug those values in by hand if you want to do that. So new x equals z, boom, 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 0, 0, 1. Y prime equals y, so there's a 0, 1, 0, so it just selects the y value, and it's not doing anything else. And the z value is then minus x, so there's a minus 1 there, 0, 0, so minus 1 lots of x's and 0 lots of those. So, not next week, but in a few minutes, we'll be doing Denavit-Hartenberg. And to be consistent with that, there's some rules that are very, very important when we're doing the analysis. And if we want to be able to do Denavit-Hartenberg analysis, we have to follow various things, conventions. But, it's good to follow conventions anyway. I suggest you always use these conventions if you're putting frames down, even if you don't want to do it with Denavit-Hartenberg, even if you want to actually do it from first principles. But to be honest, when you're doing this kind of analysis, it's good to do it in a couple of different ways, and then maybe even try it in MATLAB just to make sure you've got it right. If you're building a real system, you wouldn't want to just, scribble on the back of an envelope what you think the forward kinematics are, then type it in, and then have this huge robot do horrible things to the wall or something. So, here are 4 rules that are really important for Denavit-Hartenberg. First of all, the z-axis, I've said this before, is placed along the direction of rotation or of movement, right? So if it's a Revolute robot, z-axis is along the axis of rotation. X-axis has got to be perpendicular to the current and also the previous z-axes, right? That's very important as well. Given that we've put the z in, given that we've then put the x in, we then use the right-hand rule to put in the y, right? So you then, the direction of your, your x and your z. Make sure that you use your right-hand rule to put in the direction of the other one. Don't just guess it. Make sure that you've actually thought about, does it follow the right-hand rule? Because otherwise you might find you've put it in the wrong direction. Another thing is the x-axis has got to intersect the past z-axis. And these rules, why they're important is because we're going to, Denavit-Hartenberg is going to consider the transformation being built up from what we call two screw displacement. So it's going to be a screw action. It's rotating and shifting, rotating and shifting. We'll come to that in a bit more detail. So always place rotation about z-axis. So here we go. Let's analyse now a Revolute axis, which is going to rotate around the z. So in goes our z-axis there, right? So we're going to rotate around there. So I'm going to put this in using the right hand rule. So we've got X going off to the right. I generally would always, if the robot's going to be going that way, it's good to point and kind of in the direction that the robot arm is going to be in. I'd say you are sort of have a lot of freedom to put the first point in like this, the first frame. So X off to the right, Y then going into the plane, and Z is the rotation axis, so we're stuck with having that along the axis of rotation, right? Always follow the right hand rule for these things. And then positive rotation around X is determined by the right hand rule as well. So the direction of the thumb is the axis, so positive rotation is the direction of your fingers, so that's just important to make sure you've got that right. It's nice if everything's very consistent, and it makes life a lot easier when you're doing analysis if you don't have to find out where you've accidentally put the sign in wrong. So prismatic movement, again, is also along the z-axis by definition in Denavit-Hartenberg. And again, we put in the z-axis as being the direction of movement. And then we have to put the other two in so they're consistent, right? So we have to use the right-hand rule again to make sure that we're actually doing it in a consistent way. And then direction of displacement, of course, is going to be the direction of the axis there. So put it in with the right-hand rule, and hopefully that'll be good.